Okay, so we're going to get rolling, everyone. Welcome to the PacVec seminar series for May 27th. Just as a reminder, we're going to have another one on June 10th, same time, same place. But I think you'll have to register to get the updated link. But it's my pleasure to present the first talk, and this will be by Dr. Nick in his lab. So Dr. Nick's group operates two different laboratories, the Vector Behavior Lab and the Mosquito Research Lab, both at CSU San Bernardino. Dr. Nick's research projects and the folks who are working on these research projects, they're funded both internally and externally. They concentrate on exploring the impact of agrochemicals on various aspects of mosquito behavior, development, survival, physiology, and fitness for the transmission of pathogens. The lab group comprises both undergraduate and graduate students. And two of his students we have the pleasure of hearing from today also, Daniel Alcero and Gabby Rojas Norris will be presenting as well today. So I will hand it over to all of you. Thank you.
Thank you. Hello, everybody. I'm Daniel Alcero,
And I'm Gabby Rojas.
and we're going to present to you guys our summer training program for vectors and vector-borne diseases, led by our PI, Dr. Nick. And we're just going to give you a breakdown of everything happening towards the beginning and everything in between. So, without further ado, okay, you guys can see my screen, right? I'm just making sure. I believe so. Right? Okay. So our outreach strategy started off by making a flyer on Canva, and this flyer had a QR code, and this is how we were able to interact directly with our participants. This was sent out to all local campuses, not just limited to CSUSB, but mostly everywhere else. Dr. Nick distributed amongst his own community college through his connections, as well as me and Gabby through our classes, friends, and we just wanted to get it out there, get the word out there. And a QR code was our direct connection to our participants. And a little statistics at first glance were we had a total of 30 applicants and from 7 different institutions and 12 different majors or interests. And the majority of them, 57%, heard from a professor and staff member.
So our participation selection process included selecting 15 students from various institutions, and we wanted to focus on undergraduate STEM majors so that we can promote students to choose a career in vector control. We also gave priority to community college students so that they get more of an idea of like things they could transfer into. And a part of the selection process was sending out emails to communicate effectively with those who were accepted and waitlisted so that we can gather our roster of the 15 students we could accommodate, and just give them the information of what they need to know, where they need to meet at, what they need to bring, and so on and so forth. And some of our program arrangements included giving them hands-on experience through being able to access our mosquito research lab here at CSU San Bernardino. And each week they get to go on field visits to various places. And a bus was provided for our first field trip to Northwest Mosquito and Vector Control District in Corona. So that was very nice. And there's also a $300 incentive awarded upon completion to each participant. And we were also able to secure parking permits for all participants and daily lunch so that they don't have to worry about the cost of that.
So here's a breakdown of our actual schedule. Some things have already passed, but majority of them are yet to come this week and next week. And a little breakdown of it, we'll get into more details in depth in a bit, but it was broken down into a lecture portion, and then after this lecture, it was separated by a lunch that was provided by the program, and then they would get hands-on training after this lunch. And every Friday we try to make it every Friday there was a field trip. So last week we went to Corona. This week we're planning to go to Ontario, and next Friday we are planning to also go to Riverside, UCR. But we'll talk about that in a bit.
So our week 1 outcomes included handing out a pre-assessment on day 1 so that we can see where they're at. And on the lecture half of things, we introduced the basics of vectors and vector-borne diseases. And on the lab half of things, they were able to practice mosquito rearing and start their mini research projects. So we have 3 groups, and each group is focusing on something different, just something where they can see a change. Like the first group is going to be testing different sugar solutions on the adults. The second group is going to test larval density and how that affects their growth or their survival rates as well. And the third group is going to test how much is being fed through like the frequency of how they're fed. And then on Friday of last week, we visited Northwest Mosquito and Vector Control District in Corona, California. More about that in a bit. So here are our pre-assessment results. We collected the average and the median so we can compare it to the post-assessment results at the end of training, and we'll use this information to see what they're retaining. So our Northwest Mosquito Vector Control District visit included an introduction to vector control from the staff there. And it was a perfect transition into week 2 as well, because they told our group a little bit about IPM, integrated pest management, which is something we'll be talking about this week. And after we got to meet some of the staff, we went on a facility tour and saw some of the materials and devices that they used around. And our group also got to experience some hands-on education with pesticide application, mosquito trapping techniques, and identification of mosquito species.
And week 2 is happening this week as we speak. This week, they're going to learn about vector surveillance and control techniques, and they're going to continue their laboratory research projects in our lab. We're going to be roughly halfway through by the end of this week, or further, if anything. And surveillance and control assessment through our lectures. And then finally, like last week, Friday, we get to visit West Valley Mosquito and Vector Control District in Ontario, California. And finally, our last week, we're focusing our lectures more on learning identification of common vectors, such as differentiating Aedes from Culex and Anaphylis, so on and so forth. Learning how to work with ID keys. And we're also going to, the project should be done by next week, and the students are going to present their projects and data, and then they're going to do a post-training assessment as well towards the last day, to see their difference between their knowledge in the beginning and towards the end. And then finally, they're going to visit UC Riverside Entomology Department in Riverside, California. And I think that's going to be very important because some of these students are still deciding what they want to do specifically, where they want to go. And this would be a perfect opportunity to kind of get some networking in, talk to staff and faculty that are directly related to this entire program, and the goals of this program. So it would be it's going to be very important for them to see this aspect of the program.
So our short-term goals is we want to evaluate knowledge retention through the post-assessment that we will hand out later. And that will help us expand our program in the future to see exactly like what questions are they improving their scores on, and what questions they might not have retained as much from this program, and then we'll adapt after. And we want to facilitate student learning in vectors and vector-borne diseases. So basically, we just want to encourage students to choose this path. And at the end of our program, we're going to recognize our participants with a certificate of completion and a $300 stipend.
And now for the long term, we don't want to keep this just a short term. We want this to go further than just this program alone. So we want to establish an annual training program so that students hear about this program and have the opportunity to apply the upcoming year. And we also want to expand our outreach to more campuses and underrepresented groups, as well as increase accessibility to all participants. I think it was very nice to have students have their own lunches, forms of transportation, and make as much accommodations as possible to make this flow smoothly. And we also want to inspire students to pursue careers in vector control. There is a lot of we need more people to know about this topic, about vectors and how to control them. And this would encourage students to continue their education in public health entomology. And here are a couple of acknowledgments. People, this program wouldn't have happened if it weren't for these programs or individuals. The Pacific Southwest Center of Excellence in Vector-borne Diseases, PacVec, Center for Disease Control and Prevention, and CSUSB Department of Health Science and Human Ecology, as well as Jennifer, our Health Science Department Coordinator, and Tori. Thank you to all these people who have helped us and supported the program, and it wouldn't be possible if it weren't for these list of people. Thank you, everybody. And do you guys have any questions?
Thank you. That was great. Let's see if we can try to. Do we have any initial questions? I have a question. I was wondering, so, you always sort of think about how when you initially you're a learner, you're a student, and you're learning things in the class, but then you get to move into sort of like this teaching assistant or teaching kind of role, and that helps you obviously learn and solidify like a lot of these foundations even more when you're actually teaching it to somebody else. For the two of you, what do you feel like is the biggest takeaway for you from this program?
Well, I'll go first, but it's been really interesting to really because I've been in this lab a lot longer. It's been very satisfying to be in the lab, do everything, but more importantly, be able to teach it because the only way to assess your own knowledge is to teach it. And I did see my own flaws in ways of teaching, and it encouraged myself to push myself further in learning about my own area. And I think that the biggest takeaway from this entire project is to just assess how much you know and how much you don't know. And I think that's been the biggest takeaway for me.
Yeah,
Great.
for me, I would say learning, I guess, easier ways to train people, because for our lab, I kind of I'm newer than he is. He's been here for like 2 years. I've been here for 6 months, I'd say. Um, and for our lab, when we introduce new people, uh, it's kind of like students have to help out other students to learn how to like integrate them into our labs. So I would say that this program has helped me figure out a little bit more how to exactly to do that, because it's not easy to just make a student jump into the lab. There needs to be more of like a structure to it.
I think that never goes away either when you're teaching, right? Like every time you teach a new course, it's just you're jumping right back into that all over again. Um, so that's great. One other question that I had is I was curious what the acceptance rate was. So you said there were 15 who were part of the program. How many applicants did you have?
30.
30. Okay. So there's quite a desire for like people really want to get into this field, it sounds like, in its curriculum. Well, good job. Are there any other questions out there?
If I may say something, Crystal.
Yeah.
Okay. We had 30 applicants and we decided to choose 15 because we had to provide them with, mail and parking permit and all those things. And we could not really get all 30, and also the space and lab space and all those things. That were logistically a little bit difficult. But we tried to diversify our applicants. So from as many institutions as we could and with different backgrounds, especially, the training is focused on STEM students. So, and I think there is more chance for a STEM student to pursue education in this field or apply for a job later on to the vector industry rather than, for example, we give training to somebody from philosophy or theater or something like that. So if of course had more opportunity like fund or all those things, it could even give them a chance to come to and learn more about vectors. But when there is always a limitation, in everything, then we gave priority to STEM students. Most of them were in biology, chemistry, like public health, environmental health, or such fields. And I think it will be very useful for them eventually because there is a higher chance for them to continue their education if they're coming from community colleges or if they're doing their undergrad later on, pursue their education towards a master's degree, going to graduate school, and also at the end having a chance to work for any of those vector and vector-borne diseases agencies, either districts or county or state or at any other level. So hopefully at the end make them interested and they, at least some of them, if not all, and they continue this path. And this is what happened with our previous training in 2023. Out of the 10 applicants we had, two of them eventually got into this, and one of them is right now working with Coachella Valley Mosquito Working Control Listing, and the other one with the Northwest, the agency that we just visited on Friday. So hopefully this time we see the same thing, either with education or with the work, and both of them are good. If we see that, if we see such a thing, actually, it shows that our training has been very productive and we got the goals.
Yeah, for sure. Yeah, those are some big success stories. And I think also every time after I watch one of your talks or your students give talks, I'm always thinking, man, I wish I could go take these classes. We do have a question in the chat from Jessica Coolidge. They ask, did the students have a favorite activity during the tour at Northwest?
So we it was there was a lot of cool things happening. Whether it was like these insane like modified vehicles for pest control or the different strategies. There was a lot of things that everyone at one point everyone was like, all right, this is really cool. But I think the best thing that we all saw was they have their own little lab there for identifying whether a mosquito has a virus or is transmitting some kind of thing. I think that was like their favorite thing because right here we're on campus, we're doing our own research projects, and it pretty much all we can do is kind of say, okay, this is gonna help us out there, but in that lab over there, that is out there, and they're directly applying what we're learning here over there into the lab, and it's like I mean they get paid to do it, and more importantly they have this result right there. Like if you know how to maintain mosquitoes, this is exactly what you can do with it after. And a lot of people were interested in the end after they saw the lab side of things, like, oh, this is how you identify them. We use this to separate RNA to identify, and like so many cool things that they saw. But I think that lab portion in the district control place, that agency, that was probably their favorite part.
Yeah, that's personally my favorite part, but I will say my group was very entertained by getting to use was it water? Like,
The hose, the
the
power hose.
Yeah. They were very excited about that. Some of them wanted pictures.
It's what they use to
To
apply pesticides, and it was a really cool field trip overall. Like it's you wouldn't imagine that kind of thing going into a job that you would be doing lab research but also field work as well, identification. It's just to me personally, I have a lot of interest in this, and I can't speak for the other students, but for myself that lab portion was definitely like just it was just amazing. I really enjoyed the seeing their lab.
Amazing. Thank you. All right. Anybody else want to add anything? Okay. Thank you so much. Great work. And it's so good to hear about your program. We're going to move along to the next talk. Let's see, Talia, do you want to load up your presentation? Great. So the next speaker that we're going to be hearing from is Talia Wong. She's a PhD candidate in epidemiology in the epidemiology graduate group at UC Davis, and she's a member of Chris Barker's lab. Her work focuses on West Nile virus spatial modeling and local vector control. And Talia, we'll hand it over to you.
Great, thank you. Hi, everyone. I'm excited to share some of my work. This is going to be a little bit of shift in gears. We're going to be talking about modeling. For those of you who were at NVCAC, the beginning part of this presentation might be a little bit of a refresher, but then I'm going to move on to some of the new work that we've been doing. So the topic for today is fine-scale modeling of West Nile virus vector dynamics to inform vector-controlled trial design. When I say fine scale in this context, what I mean is a high resolution spatial scale. And the reason that this matters is because we want our modeling efforts to matter, be relevant in sort of the real world of public health and vector control. And most models for West Nile virus risk are built at coarser scales, for example, at the state or county level, whereas vector control is implemented more locally, on the city scale, for example. And so what you see here on the panel on the right is an outline of the city of Davis, and each of those colored polygons are where sprays occurred in 2023. So the models that I'll be discussing today are focused on understanding and using spatial factors on this high resolution scale to anticipate West Nile virus activity on the city level so that these models can be useful for making actual decisions about where to spray or where to place a control trial for maximum impact or to get maximum data. Spatial features are useful for a few reasons. One, they remain largely stable over time, and many changes that do occur, things like maybe new construction or new agricultural layouts, can be accounted for in advance of the implementation of any vector control effort or trial. There's also good evidence that spatial factors are highly influential when it comes to vector dynamics and vector-borne disease. This paper is an example of that. This figure is pulled from a 2004 paper by Smith et al., where they looked at theoretical distributions of mosquitoes and measures of vector risk, specifically prevalence, under different spatial contexts. So if we look on the left, here we have a point source of mosquito emergence represented by this little larva. And we have a homogeneous distribution of our blood meal hosts represented by the shaded gray bar. And in this context, we might expect adult mosquito abundance to steadily decrease as we move away from their point of emergence. However, we might expect something like prevalence under the assumption that mosquitoes age as they move away from where they emerged. We might expect something like prevalence to increase. If instead we completely change the spatial context, and here we have a constant source of emerging mosquitoes and a heterogeneous distribution of our blood meal hosts, we get a new pattern of both our vector abundance and prevalence. And kind of the interesting point that I want to draw your attention to is this spike in vector abundance and even prevalence that we see at this edge where host density switches from low host density to high host density. So the point of this is just, again, that spatial features do matter and they influence two of the most important components when it comes to estimating risk, which is our vector abundance and our vector prevalence. And so here we see how those spatial features can translate to real data. So my work is focused on Davis, California, and around here our primary vectors are Culex tarsalis and Culex pipiens. And so when we think about, what our point sources of larvae are here, particularly when it comes to Culex tarsalis, we have many rice fields that surround the city of Davis, which you can see circled here on the left in the blue pixels. So these, to me, are a good sort of translation from that theoretical point source to an actual point source. And then when thinking about that stark change from low host density to high host density, we suspected that this urban agricultural edge might be a good representation of that jump. Again, low being sort of outside the city and then denser host distributions within the city. And under this assumption, we then might expect that our mosquito abundance and prevalence would be higher along the city edge rather than within the center of the city. So I wanted to build a model to look at the associations between these variables and mosquito abundance and prevalence. And so to initialize them, for those point sources of larvae or the rice fields, I decided to use the area of rice within an 8-kilometer radius of a given trap site. This would allow me to account both for the proximity of a larval source as well as the abundance of that larval population. And then to look at the effect of the urban edge, I decided to look at the distance between a given trap site and the urban edge. Again, under the suspicion that adult females might tend to congregate along the edge of a city rather than penetrate into it. Some other spatial variables that I was interested in, both because I thought they were interesting by themselves, but also because I was concerned that they might act as confounders for my main variables of interest, were land cover types. I use the National Land Cover Database categories for this. So there's 4 different levels of urbanization, from high, being very densely urban, all the way down to open development, which would be things like, city parks, and then cultivated crops, water, and wetlands. And I was also curious if imperviousness was going to be an issue, that being sort of the amount of impervious land in a given area, things like asphalt and concrete, for example. And the rationale behind this was that both of these could affect mosquito habitat suitability. They could impact host availability and diversity, and they could also affect the experienced temperature by mosquitoes in those areas. So, in order to build these models, we needed really good data to go along with it. And so in 2023, we conducted this field study across Davis. We trapped mosquitoes along the 5 transects that you see here. And the goal in creating these transects was to create a gradient in those spatial variables. So a gradient in the amount of air, amount of rice contained within that 8-kilometer radius, and then a gradient in terms of the distance to the urban edge. And we trapped every other week for 3 months from July through the end of September. Once mosquitoes were trapped, they were brought back to the lab. Males and other species were recorded and then discarded. And then Culex tarsalis or Culex pipiens females were saved. Those that were blood fed were stored at -80 for future blood meal analyses, and those that were unfed or gravid were pooled for West Nile virus testing by qPCR. I did put Culex pipiens in parentheses here. As I'd said earlier, they are one of our major vectors, but unfortunately, we just didn't get high enough sample sizes to use them for modeling purposes. So from here on out, I'm just going to be talking about Culex tarsalis. The first set of models that I built were inferential models. So my goal was to understand the relationships between these spatial variables, and in this case specifically, Culex tarsalis abundance. Again, at MVCAC, I did talk about the prevalence models as well. Today, I'm just going to be focusing on abundance because that's kind of where we've made our next big strides forward. So in this first model, we're looking at the association between area of rice within that 8-kilometer buffer and Culex tarsalis abundance. And on the left, what you're looking at is the tensor product smooth of the area of rice interacting with time. So there was evidence of an interaction between these variables in the model. And this heat map's kind of useful, I think, because it's pretty intuitive. So red would be a positive effect or an increase in abundance, blue being a negative effect on abundance. And so you can see as we move from left to right, or we increase the area of rice within that radius, you get an increase in overall abundance. And then as we move from the bottom to the top, which is to say we go deeper into the season, we get a cooling off as there are fewer mosquitoes. We can also take this tensor product and break it into the marginal effects, which we're looking at here. So this is the marginal effect of area of rice and of time. And here you can see again, as we increase our area of rice, we get an increase in abundance. And then this particular year, we saw sort of a steady drop off in our numbers of mosquitoes from July through September. This is the second model where I was looking at the relationship between the distance to urban edge and abundance. And again, here we can look at this representation of the smooth. We have kind of the opposite effect. So as you increase your distance from the urban edge, that is, you move from the urban edge towards the city center, you get a decrease in overall abundance, and the effect of time is the same as we saw before. And again, just for ease of visualization, we can break this apart, and you can see this negative slope. So as you increase your distance from the urban edge, you're going to get a decrease in abundance, and then the same effect of time as before. So to summarize our findings from these inferential models, being closer to the urban edge or increasing your area of nearby rice fields will be associated with higher Culex tarsalis abundance. We also learned that the effects of these spatial variables are time dependent. So the strength of these spatial effects is going to differ depending on when in the season we're looking. In terms of the implications for vector control placement, these models suggest that even within a city, not all areas are created equal. And so to maximize the power of a given vector control study, it is useful to consider comparing your treated and control groups within predefined spatial strata. And this is actually exactly what we've been doing for an ongoing trial that we started last year, and that we'll be wrapping up this year. We used what this model told us about the differences in mosquito distributions across the city to create spatial blocks within which we assigned our treated and control stations, so that within each block, we could expect that prevalence and abundance sort of baselines would be similar. And again, the whole benefit of this is that it maximizes our ability to detect a true effective intervention or study power. So the next step for these models is to see if we can move from inference to prediction. Can we take what these models showed us about which spatial variables are important, combine them with other variables that influence abundance and prevalence, and then project what the distribution of mosquitoes and West Nile virus prevalence might be across Davis in a future year. And again, this would have potentially important implications for vector control, as you could anticipate where and when to treat, or when and where to place a trial for a given year. Making this jump from inference to prediction is not a small one, and we had sort of a threefold goal. We wanted to build a model to predict Culex tarsalis abundance, build another model to predict West Nile virus prevalence in Culex tarsalis, and then finally combine these into a joint model to predict vector index, being one of the most useful measures of risk for vector control. We also decided to transition from a frequentist approach to a Bayesian framework, and there were a couple of reasons for this. One, when it comes to modeling something like vector index, which is a product of abundance and prevalence, things like confidence intervals become pretty tricky. And so using a Bayesian model allows for credible intervals, which are a little bit easier to work with and also more interpretable, which was nice. And then the other benefit to a Bayesian framework is that Bayesian models can be updated with new data. And so this was appealing to us as well. In terms of the variables I was interested in looking at for this prediction model, we were going to use some of those same spatial variables that we looked at before. So area of rice, distance to urban edge, and the proportion of each land type. In addition to these things, having evidence that these affect things like abundance and prevalence, there's also the fact that without this, our model would not have been on that fine scale, which is the whole point of this project. It would sort of just have predicted for all of over Davis, which is not our goal. And then we also looked at some variables that would affect nightly variability in mosquito numbers, for example, things like nightly wind speed and nightly temperature. And then we looked at some variables that could affect seasonal trends as well as year-to-year trends. So cumulative degree days over 14.3 degrees Celsius for the prior 2 weeks, 14.3 degrees Celsius being the threshold at which West Nile virus will replicate. Again, to sort of look at overall temperature trends. And then cumulative precipitation over the wet season, as well as the fraction of that precipitation that occurred late in April and May. The data sources for this, I used VectorServe for all of the mosquito data, and we used data from 2006 all the way through 2024. Weather variables were sourced from the California Irrigation Management Information System, or CIMIS. And then a special shout out to Ruben Rosas for his help. He provided all of the rice field shapefile data that I used from 2006 to 2024. And then again, I got all of my land cover data from the National Land Cover Database. This is what the final prediction model for abundance ended up looking like after testing out each of these variables. So abundance was dependent on spatial variables, which included the distance to urban edge and the area of rice. Weather variables, which included those nightly variation factors like the temperature, nightly temperature, and nightly wind speed. We incorporated sine and cosine terms for week of the year to account for seasonality trends in abundance. And then there was a significant interaction again between area of rice and time in this model. And then finally, the model included random effects for site to account for repeated sampling, as well as a random effect for the year to account for year-to-year variations that we weren't already sort of looking at with the variables that we included. And then the model also included an offset for the total number of nights that a given trap was set. We can start looking now at the marginal effects of these variables in this model. And first off, very encouragingly, the effects of our spatial variables are the same as we saw in our frequentist inferential model from previously. So as you increase your distance from the urban edge, you do see a decrease in the expected count of Culex tarsalis per trap night. And by contrast, if you increase your area of rice, you will see an increase in your expected count. And now we can look at those weather variables. So as you increase your overnight average wind speed, assuming that you probably are causing disruption of Culex tarsalis dispersal, you're going to see a decrease or have a decrease in the expected count of tarsalis. And as you increase your overnight temperature, you see an increase in the expected count. And this is, again, probably due to increased activity. And we can start creating some really cool and insightful graphics, I think, to understand how these variables work together to influence Culex tarsalis abundance across the city of Davis. So on the left, we're looking at three different amounts of rice, red being above average amounts, green being the mean, blue being below average amounts of rice within that 8-kilometer buffer, and then seeing how the expected count of tarsalis changes over time. And so you can see, unsurprisingly, if you have a greater than average amount of rice, you're going to have overall a higher expected count than you would in the other categories. But what's also interesting in this figure is you can see that the shapes of these curves change, right? And this is just a reflection of that interaction between the area of rice and time that we mentioned earlier. We can also add in another variable to the mix, which is what I've done on the right. So for this figure, I took the 90th, 50th, and 10th percentiles of the amount of rice or area of rice and distance to urban edge, and then faceted this particular graph over your distance to urban edge. So again, you're looking at the effect of different areas of rice across time, and you can see that within each panel, the pattern is quite similar to what we saw over here. But what I think is neat here is you can see that as you move from being close to the urban edge to being far from the urban edge or towards the city center, you see that the overall counts decrease, right? Which is reflecting that negative effect of moving away from the urban edge. Finally, we can synthesize all of this information from the model to generate a map of the expected Culex tarsalis abundance over Davis under different weather scenarios. This scenario is sort of the worst case one. It's where we have very high average nightly temperatures and low winds. I usually think that the worst case is often the most interesting one to look at in a model. And so we can see towards the beginning of the summer, it's a relatively low abundance, right? Towards middle of the summer, we get a peak in abundance all across Davis, and then we start to cool off again towards the end of the summer. And what I think is particularly interesting in this graphic is that you can make out this, dark core or differently colored core in each of these points of the season, which illustrates that effect of the urban edge, right? We have this band of sort of increased abundance at the edges, which again is that urban edge effect. Another cool way to look at this is to add in our rice polygon shape files. This is specifically where rice was planted in 2023. And I think this really highlights why East and North Davis are such hotspots for our mosquito abundance. They are the closest to the most amount of rice, especially when you look at the alternatives towards the West Davis and South Davis. So moving forward, the next step is going to be to develop a predictive model for West Nile virus prevalence in Culex tarsalis, following kind of the same steps that I did for abundance, and then to develop a joint model using both the abundance and prevalence models to develop that predictive model for vector index that I mentioned earlier. And then finally, I'm going to be performing external validation for all of these models by testing them against new data. So data from Davis this year, which was not in the training set, obviously. And then also looking at the model's generalizability to cities that are similar to Davis in terms of their agricultural context and their primary vectors. And so specifically, I'm going to be seeing how the model performs against data from Woodland. With that, I just want to say thank you to my funding sources, to Chris Barker, Sakiolo, and Ruben Rosas especially, as well as everyone else who's been helping out with this project along the way.
Great, thank you. That was an excellent presentation. I see we already have one question in the chat, so we'll take that one first. Anthony Smith asks, did you also take breeding source data as well? Water level, water temp, site description, etc.?
Yeah, so I'm wondering if that is in reference to specifically like breeding sources like the in the rice fields themselves, or if we're talking about looking at other potential sources. In terms of we did not is the answer, but one thing I have considered is, should we be taking a look at other potential breeding sources within the city? At the moment, the answer is no, only because the rice is so dominant here, and we think that that is our primary source of our vector. But it's a good question, and it would be interesting to look at some point.
Okay. I had a question. So maybe this is my me being naive that's going to come out, but anyways, we'll ask it. We'll ask it. So when you're talking about distance to urban edge, that's all it's distance within the city to the urban edge, right? Not distance outside of the city to the urban edge. I was wondering if you thought you might see the same effect, like if you were to do trapping outside of the city but close to the rice fields. What do you imagine you might see in the rural landscape?
Yeah, that's actually a great question, and I have thought about this. So when I first started kind of playing around with this data and just visualizing abundance, numbers basically by traps before doing any modeling, I did use some of the data from outside of Davis. The problem with that data is it's very sparse, and usually the traps are set out for many, many nights, and so it's not the most reliable data. But even with that sort of sparse data, it did look like the effect of the urban edge was a bit of a tent. So if you moved away from the city outside of Davis towards the rice, you actually still saw a slight decrease in abundance, which was fascinating to me. But again, that would fit with the theory that mosquitoes are sort of moving with the goal of seeking a blood meal host. And when they hit that urban edge, they reach a high density host population. And so that's kind of where they're going to stay. But I would love, I mean, if we had the resources and the time, I would love to trap, sort of in transects moving out of the city as well and just see what that looks like.
Great. Thank you. Let's see. Any other questions from the audience? Okay, I had one other question. So for my other question, I was wondering, so you brought up imperviousness, like concrete and that sort of thing. I know that this wasn't really discussed in your presentation, but I was curious, have you looked, so you had like, you have two big sort of highways that are going through Davis. And I've always wondered when I think about Maricopa County, for example, and all of the big interstate or the freeways that are running through the county, I wonder often if the mosquito likes to cross the big road. And so I was wondering if you do see effects due to those larger roads versus maybe the smaller ones that you might see inside of Davis.
Yeah, that's another good question. And it is also something I've thought about because I do wonder sort of if the mosquito won't cross the road just because there's not much reason for it to. Um, and again, I think the other thing that happens is once you hit those highways, you're sort of going towards the middle of the city anyway. And so you see that tapering effect of the gradient of abundance. And so it's so sparse really by the time you get to that area that I don't know how well you could measure what it is as you keep crossing the highway. Um, but I mean, it's still a good question. I don't have a straight answer. The other problem with it is, it would be extra interesting if we also had rice, let's say, on the south part of Davis, because then you could see if like, you have this gradient and then there's like a split over the road. That would be fascinating. But because Davis isn't really built that way with the surrounding rice fields, I just don't think that we'll be able to make that determination of how much of an effect the road's having. But we have thought about it.
Yeah, that all seems very reasonable. I think about it too. So, all right. So it looks like we have no more questions, but I want to thank both of the speakers for just doing a really excellent job. This was great to come to, and then also would like to remind everybody again that the next PacVec seminar will be on May 10th. And we're going to be hearing talks from UC Irvine, mapping mosquitoes, how to data and models help us understand vector risk. And then also at UC Davis, healing the marsh, healing ourselves, co-creating vector smart wetlands with traditional ecological knowledge. Right. Thanks, everybody.